Last part is about second order circuit, step response for parallel RLC circuit. Okay. And we will see here that unlike the source-free parallel RLC circuit where we calculate the voltage, here we calculate the current for the same reason of the step response of series RLC. If we have this circuit here and we want to solve it, we apply Kirchhoff current law. So this current IS equals this current plus this current plus this current. So V over R, this is the current in the resistor, equal plus 1 over L integration of V dt. This is the current in the inductor, plus C dV by dt, which is the current in the capacitor. Okay, equal IS, of course. So if we want to differentiate this, we will lose IS. We'll lose it. So what we need to do here is to use this equation here and replace V by I. I is the current in the inductor. So actually, instead of having this, we replace this just by I. And V over R, we replace V by this value here, L di by dt. And here, we instead of V, we replace V by L di by dt. And by doing that, we'll have a second order differential equation in I, and it will look like this. And then after we substitute by V equal L di by dt, and then divide by the constant LC, then this will be the equation. And we convert it to this form. Okay, so in this case, alpha equal 1 over 2 RC, and omega 0 equal square root 1 over square root of LC. Okay, then in this case, this means that, of course, you have two solutions for this equation. That you have a transient solution and steady-state solution. Then I of t equal IT transient plus ISS, the steady-state current, the steady-state current. The transient is exactly the same like previous solutions. So IT of t equal, here if it is over-damped, critically damped, if it is under-damped, so like what we did before. So we just use the initial conditions to calculate A1 and AT and A2. The steady state, this is the current at infinity. Steady state as a current at the infinity here. So for example, if this one here at infinity, the capacitor is open circuit, the inductor is short circuit, so it will short the resistor, then all IS will go through the inductor. So the current, the infinite current here is this IS. This IS. Then what we need to do is just calculate both steady state and transient and add them. This will be the current. Okay, so there's nothing here new in this slide. It is the same. So IT of t equal, if it is over-damped, this is how it look like. If it is critically damped, this is how it look like. If it is under-damped, this is how it look like. This is the transient part. And then you add the steady state to get the total current in the inductor.